Good morning and welcome. On the homepage you might have seen the note giving some information about the coming weeks. So this is regarding the exercises and also the contents of the lectures. You have to adjust a little bit because many of you will be on excursions with your study programs, especially in the week before Easter. So the other important thing is to note the deadline for having at least 9 out of 12 exercises approved. And this deadline is set to the last day of the course, which is April 21. So then you should have at least 9 out of 12 exercises approved. Do you have any questions regarding the organization? If not, you can also address one of us, Rada, one of our teaching assistants, it's Alexander, or Jürgen, or me, or one of the reference group. We'll have a meeting next Wednesday, the reference group. So that is this, and now we want to continue, and the topic that we are going to deal with this week, and in a certain sense also next week, regarding the solution, what we get for when we do discretization, that is the Poisson equation, that is elliptic equations, elliptic PDEs. So first we want to see what is the Poisson equation, what is the physical origin of it, and its mathematical classification. So then we start with that as usual, with the physical and mathematical classification. So the Poisson equation is due to Siméon Denis Poisson. And it was devised or published by him the first time in 1813. And it looks like that. We have the second derivative of our unknown function, which is a function of in 2D of x and y with respect to x squared, and we add the second derivative of the unknown with respect to y. And on the right hand side we have some source term which usually is of this form. It depends just on x and y. So and we assume that x and y, which is our vector, that is in some domain omega. This is then, was then later called after Poisson, it's the 2D Poisson equation. So that is in the 2D Poisson equation. We just refer to it as the Poisson equation because we restrict ourselves to 2D. But you could do it in 3D, that we have also interesting applications in fluid mechanics on that. And you could even do it in multi-D if you would like. So, if the right-hand side, well, the omega, maybe I should give you just an indication of that. The omega is just a domain. So we have some domain omega, and we shall denote the boundary of omega, we shall denote by d omega. Okay, so if the right-hand side of the equation, which is x, f of xy is 0, in the Poisson equation, we get the 2D Laplace equation. So then it becomes the 2D Laplace's equation. So there are different ways to express it. Laplace's equation. that is then the second derivative of u with respect to x plus the second derivative of u with respect to y is equal now to 0. And that is again for x, y in the domain that we consider. And that is then named after, again, also Poisson, who was a French mathematician and physicist, also Laplace. Let's see, Laplace, well, Poisson was the younger one. Okay, so we have seen in the very beginning of the course that this type of equations, they describe some equilibrium problems. And they have also a name of jury problems because they are essentially determined by the boundary conditions. So from outside, the jury sitting around decides what is going on in the interior. We might have different boundary conditions with that. And there are three main classes of it, which we want to see. And we have already seen two of them. That is the Dirichlet boundary conditions and Neumann boundary conditions. We have discussed that when we discussed the heat equation. So we have here a similar thing. So, boundary conditions. So as usual we use the acronym BC for that. And the first one is then the Dirichlet boundary condition. So we say that u, I do the notation like that, that is u on the boundary of the domain is equal to some given function g. So that means that the value of u of the solution on the boundary is given. So that means we shall understand when we write this that it means that u, our solution to the Poisson equation, is equal to some given function xy for xy on the boundary of omega. So that is when I use this notation. And this is called a Dirichlet boundary condition. So that we have already seen. When we, however, do not give the value itself, but its normal derivative, then we get a Neumann boundary condition. So that is then the other possibility. That is when we have du dn on omega is equal to some given function g. And that is supposed then to mean the following, that the normal derivative can be expressed with the x component of the normal vector. Then we have the u dx plus the y component of the normal vector. And that is then equal to g. Say I write it in this form. Here we should also write everywhere of xy. I don't write it. That would be for xy on the boundary of omega. That is called a Neumann boundary condition. So what is meant by this normal here? Again, we have the domain omega. We have the boundary d omega, so that's this one. And the normal, that is when we have at some point we look for the tangent, and then the vector normal to that is n. The vector has the components nx and ny. So that is then our normal, outer normal. So in this case, not the solution itself, but its normal derivative is given. Then we have a Neumann boundary condition. And we can combine these two to give so-called Robin boundary condition. So it is then the new one that we have not yet seen. So we have then A1 times the solution on the boundary plus A2 times the normal derivative on the boundary. That is then given equal to some function g. So, and if we write it in this form, we usually assume that the A1 and A2 are not zero. Because if one of them is zero, we have either Dirichlet or Neumann boundary conditions. So this is then called Robin boundary condition. In fact, we can have also on different parts of the domain different boundary conditions. That we'll see in exercise 10, that we have at some parts of the domain the Dirichlet boundary condition, and on other parts we have Neumann boundary conditions. So then we have that. Now let us look at some examples where the equation occurs. We have already seen one nice example on Tuesday with radar, and that is fully developed flow in a rectangular duct. So we have the following situation. We have a rectangular duct. So let's assume something like that. So this is the duct, and the flow is going this way. So here we have our velocity vector, and we assume that we have the following coordinate directions, that we have the x and the y in the cross-section of the duct, and that we have the z in the streamwise direction. If we have this situation, then we assume that we have no component of the velocity in x and y. So u and v are assumed to be zero. We assume that we only have the component w in the z direction, and the flow is assumed to be driven by a pressure gradient. Imagine we have here a larger pressure than here, so the pressure drives the flow. So if we would look at that between two plates, we would have Poisson flow. But here we have a duct with real nice boundaries, and what we get, the equation that we get, will be the second derivative of the component w, which is the velocity component in the z direction, with respect to x, plus the second derivative of w with respect to y. And on the right-hand side, it will be, we write it in this form, so we write now the viscous term on the left, we divide by mu, the viscosity, the dynamic viscosity coefficient, and then we assume that we have a pressure gradient. The pressure, we assume, is constant in each cross-section, and it is varying just linearly in the z direction. So we have a higher pressure to the left and to the right, so the pressure drives the flow. So let us just note that where the pressure gradient, therefore we write it at the full differential here, is constant and negative. So, and well, I mentioned already that u and v, velocity components in x and y, are zero, and that we have a fully developed flow, so that the velocity profile will be the same in each section, so that the dw dz will be zero. You saw an example on Tuesday from Radar. You can look also at the home page where he put the MATLAB scripts. Okay, so that is then extending our knowledge on fluid mechanics. And we stay in fluid mechanics, and we learned there in the basic lecture about two-dimensional irrotational flow. And if we have that, we can have a stream function, and we can have a velocity potential. If we restrict ourselves here to 2D, so for 2D irrotational flow, we have a stream function that is usually denoted by psi. That is connected to the velocity. We can express the u as the psi dy and the v as the minus d psi dx. So then we can satisfy the continuity equation, and then to get the rotation of the curl of the velocity to 0, then we get this 2D Laplace equation. And that is the following, that we can then say the second derivative of psi with respect to x plus the second derivative of psi with respect to y is equal to 0. We saw that also with radar on Tuesday, where psi is constant, that is indicating a streamline. So this is a nice way to illustrate flow that is irrotational. So that is the basic assumption. So the vorticity is 0. We have no viscosity, so it's inviscid flow. But for that it is really nice then to see how the flow is behaving. And as Radar mentioned, it is nice then with that you can get some lift. That is okay, but you cannot get drag. We have D'Alembert's paradox for that. So you could not thrust that as long. For example, when you have flow over a cylinder or another object, then you can trust when on the front side the results, but as soon as the flow gets separated, it's no longer physics involved because their physical effects are important. Again, for 2D irrotational flow, we can also then have a velocity potential. 2D irrotational flow. The velocity potential phi, and that is connected to the velocity, that the velocity is equal to the gradient of the velocity potential. So in 2D we can write it then in this form. That again satisfies the 2D Laplace's equation, which is 6d squared phi dx squared plus d squared y squared is equal to 0. So here we have the velocity potential, and here we have the stream function. Both of them are governed by Laplace's equation. This we had in the beginning, that is the Poisson equation. Now we can also get something out of the Navier-Stokes equations themselves directly. Here we, in a sense, we also do that. But the following, if we take the divergence of the incompressible Navier-Stokes equations, by the way, what also we have been discussing here, incompressible flow. Yields using continuity equation following. So let's see what we get. So we take the divergence of first the time derivative in the Navier-Stokes equations. Then we take the divergence of the nonlinear term, which is again the divergence of rho dv, this tensor. And on the right hand side we get the divergence of the gradient, which is that is the nabla squared. It is the Laplacian of the pressure, and we get the divergence of, if we assume that mu is constant, that is an assumption here, mu is constant, that we have here the nabla squared of the velocity vector. So you see what we have done. We have the Navier-Stokes equations. You see here the terms. Here we have minus gradient p, and here we have mu Laplacian of v, and everything is multiplied from the left with the divergence. We take the divergence of the whole equation. And then we can interchange here the, let's see, I think I forgot here a row. We can easily correct that. So here should be a row, of course. Let's see. If we write it in this form, there should be a row, velocity. See, there's a row, so there should be a row. But the row is constant, and then we can interchange time derivative and divergence, and then we get the divergence of v, the time derivative of that. So that will be 0. This will not be 0, we get something. This will not be 0, we get something. But here we have the same argument. We can interchange can get the divergence inside here, and then we can get that to 0. So what we get in the end is that the Laplacian of p is equal to minus this divergence of the nonlinear term. Let's see. So we get the following. That is now 2D. So that we restrict ourselves now to that. Then the Laplacian gets the d squared p dx squared plus d squared p dy squared. And on the right hand side, so we put the minus on that side, we get then minus this term. And if we write this term, we get a d dx. And then if we write everything, we can simplify that further. But I write it now just as it comes, u v dy and d dy of d rho u v dx plus d rho v squared dy. So that is then the minus of the nonlinear term. And if we know the velocity, u and v, component in this case, then we have a Laplace equation for the pressure. A Poisson equation for the pressure. So that is, if the velocity vector that is in 2D, then uv is known, and rho is constant, then this is a Poisson equation for the pressure. That shows, in a sense, the elliptic character that we have in the incompressible Navier-Stokes equations. When we do something at some point in the flow, it is immediately felt everywhere. So that is something special. Now we continue. So this was the journey on fluids. Now we go to heat transfer, and look what we have there. And what we have there is the steady heat equation. We looked at the heat equation before, but now we look at it for the steady state. That means when the time derivative is 0. But here we make it a little bit more interesting. We assume that we have a heat source. And then we have the following, that is the general form. We have the derivative of k, dt dx. T is the temperature, and k is the thermal conductivity. So that is then with respect to x plus dk dt dy with respect to y. And we add then some source term which might even depend on temperature itself, and then that is 0. So if we would have the full energy equation, we would have the time derivative of rho Cp T, and we would have the nonlinear terms, which giving us the transport, the effective transport. But if we have only look at this situation where we have a steady state and where we assume that we have no motion, so the velocity is 0, then we have this form. So in here, the K, with units are watt per meter Kelvin, is the thermal conductivity. And the S is the heat source. ST. And if we measure that in watt per cubic meter, is the heat source. If the thermal conductivity is constant and the source, the heat source, is not a function of t but only of the spatial coordinates x and y, then we get a Poisson equation. But even in this form, it is an elliptic equation. So with the methods that we are going to discuss, for the discretization of the Poisson equation, we can also use for that. So if the thermal conductivity is constant, and the source term is only a function of x and y, then the steady heat equation, the heat source 8, corresponds to the Poisson equation. It's the following. Then we get second derivative of t with respect to x plus the second derivative of t with respect to y is equal then, if we put then the source term on the other side, that will be then of xy, and we divide by thermal conductivity, then we have this form. So, but we could also leave the k up. It depends how you like it. Okay. And when we discuss temperature, we can, in the same sense, also treat concentrations. So then we would not have the steady heat equation with heat source, but the steady diffusion equation with heat source. We would not have T, but C, a concentration. We would not have K, but D, the diffusivity. But otherwise, we would get the exact same reasoning. So these are then the examples from fluid mechanics and heat transfer. And there are also many other examples. Just in electrostatics, Gauss' law for an electric field can also be expressed as a Poisson equation. Regarding the mathematical character, if we look at the equation, we can write it as 1 times the Poisson equation now. So we have here the Poisson equation. We can write it in this form. Now with xx, the subscripts are derivatives, partial derivatives. And on the right hand side we have then something. Then we can identify the coefficients with what we discussed in the beginning of the course. Then we had then a classification of second order PDEs. The 1 corresponds to the A, the 0 to the B, and the 1 to the C. And then we argued the discriminant that we get decides on the mathematical character. And the discriminant is b squared minus 4ac. And if you put in the values that we have, b is 0 minus 4, 1, 1, we get minus 4. So this is clearly smaller than 0. And then the equation, the PDE, is elliptic. That is the criterion. So from that we can see, and that is the argument that we had in, if you want to look back, that we discussed in chapter 2, section 3. So the Poisson equation is elliptic. So then we have characterized its mathematical character. For the Poisson equation, we have the so-called maximum principle. That says the following. If the Poisson equation, now we can write it even more general than the Laplacian of the Nabla squared operator, can it not be in 2 dimensions, can be 1, 2, 3, or n, whatever you like. That is equal to some given right-hand side. If that is larger equal than 0 in the domain that we consider, omega, then the solution to this equation, u, will attain its maximum the maximum over omega. So we want to have the maximum of u in the domain omega. It will attain that maximum on the boundary d omega of the domain omega. So that is what it says. So if we have this situation, we know where the maximum is. So you can think about that if you imagine if we think about it, you can do it in general, but if we are it would be in 1D. I give just the sketch here of the proof. In 1D, if we assume that the solution u of, in our case it would be then the uxx equal to f greater equal than 0, would have the maximum inside, in the interior. Maximum in x0 in the interior of the domain, that is not on the boundary, in the interior of omega, that is not on d omega. Then we would have that the first derivative at this location, if it's a maximum, then it has to be 0. So that is the criterion for a maximum. And we have a really true maximum, we would expect that the second derivative is smaller than 0. We have a maximum, the second derivative should be smaller. But this is a contradiction to our assumption that the right-hand side is greater or equal 0. So contradiction to uxx equal f greater than 0. So then we have shown then, at least for 1D, that the maximum in this situation must be attained on the boundary. So let's see, can we understand that? If we have, let's see, we have the second derivative that is equal to f. Let's assume that we have x and we would have u. We have the, if we take the very the simple example, let's see if we have we have the x squared. So that the x squared, the second derivative would be 2. If we would have some interval here where this would be our domain omega, this here, that would then the d omega would be these points. So the maximum then is attained on the boundary. So that is not in the interior. So that is an example just for 1D. Because here we can say that the uxx here is, in our case, it is the 2, which is greater than 0, so then it falls under this situation. So then the maximum is attained not in the interior, but on the boundary, here and here. What is when we have f equal to 0? Then we can argue both that, say, for u will then attain its maximum on the boundary, but if we take it the inverse, if we take then the whole argument for minus u, that will always also attain the maximum on the boundary. Of course, then for that, with this situation, the equation will be also satisfied. So that means both maximum and minimum for Laplace equation, f is 0, will be attained on the boundary. So that we can say from this. Okay, so then we have a mathematical and physical classification of the Poisson equation. Now we want to discretize the equation. And we shall use the standard finite difference method. We consider for our discussion here a rectangular domain. We don't have a rectangular domain, then we would have to do a transformation such that we get a rectangular domain, and then we can use the arguments. So we assume that it has xa, xb as the boundaries in x direction, and yc, yd in the y direction. So we assume something of the following kind: x, y, and we assume something of that, so that we have the xa here, that is the left boundary, or the western boundary, right, or the eastern boundary xb, and the lower boundary yc, and the upper one yd. For the discussion, we shall assume directly boundary conditions. So that means we shall assume that we have at the left boundary given G, called GA, the right GB, at the lower GC, the upper GD. So then we shall discuss non-boundary conditions later. First we take directly boundary conditions. They're easier. So that is our assumption. We assume directly boundary conditions. And we can write it in the following form, that we say U of XAY, it is along this boundary here, is equal to some given function GA of Y. Likewise on the right, U of XBY is given as some function GB of Y. That is for Y in YCYD. And likewise at the lower and upper boundaries, we have the U of XYC is equal to GC of X, and U of XYD is equal to GB of X for X in XA, XB. And then we determine our grid points. And here we make a particular choice that you will understand when we, in very soon, why we do it in this way. So we say that xi, so we want to have Cartesian grid points equidistant, like we have been discussing so far. So we have xa plus I times delta x. It is not something unusual to us, that is what we have been doing all the time. But now we shall use the following. We shall let I go from 0, that is also not uncommon, but now we let go it to ni plus 1. That is a little strange, but the reason is at 0 we will have the left boundary conditions, and at ni plus 1 we will have the right boundary conditions. So our unknowns are then only from 1 to ni. That is the reason. So then we can focus on our unknowns. And the grid spacing is then delta x equal to, it is xb minus xa. So here we have ni plus 2 points. And to get the grid spacing, we have then to divide by ni plus 1. So that is something which is different from before, because we are now labeling our points differently. So let us see what this means. If we look here, so it should be equidistant. So then we do the labeling. Well, it's hard for you to see, so I can get on the other side. So by the way, this is then our domain omega that we consider in the whole. So we take the first, that is then our I is 0, this is 1, this is the one is ni, the last one is ni plus 1. So that in here we have now denoted, or we have it here, for example, we have I, grid point I, they are then on these lines. And for the y direction we do something similar. So if we then denote the j in this direction, then we would start here from 0, 1, that would be then the nj, and that last one, so that corresponds then to the nj, that corresponds to the 1, and the last one would be the nj plus 1. If we have j, that would be j here, then we would have a grid point, that would be the grid point xi, yj. So we can characterize that by the indices I, j. So I just have also to give you the grid points yj. And they are the following. So that B, the yj is equal to, there we start by yc, and we add j times delta y. And that we do in a similar fashion now from 0, 1. Now we go here to nj plus 1. Again, for the same reason, at 0 and at nj plus 1 we have the boundary conditions. So our unknowns are only from 1 to nj. And we have that then with the grid spacing. Delta y is then equal to the interval in y is yd minus yc. And we have nj plus 2 grid points, so we divide by nj plus 1. So then we have defined our grid points. Okay, discretization we then discuss after the break.